A-level statistics, factorials and arrangements. In this section we'll be looking at the number of ways that things can be arranged. These are called permutations. But to start with, we'll begin with the factorial function. Now we define n factorial, which is written as n with an exclamation mark, to mean n factorial is equal to n times n minus 1 times n minus 2 and so on to finish with times 3 times 2 times 1. So for example, 3 factorial is 3 times 2 times 1 and that's 6. 5 factorial is 5 times 4 times 3 times 2 times 1, which is equal to 120. Now we define 0 factorial as being equal to 1. Now scientific calculators will have a factorial button. It will probably be a shift button. And you can type in 60 factorial equals, and it'll give you the answer 8.320987113 times 10 to the 81. And as we can see, factorials get very large very quickly. Now fortunately, factorial expressions often cancel very easily. We're quite often going to end up with things like 8 factorial over 6 factorial. Now 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. But a lot of that cancels. And we're left with just 8 times 7, which is 56. In fact, it's sometimes useful to write 8 factorial as sum of the numbers, 8 times 7, times, and then just 6 factorial. So 8 factorial is 8 times 7 times 6 factorial. So if we had 13 factorial over 10 factorial, that would be 13 times 12 times 11 times 10 factorial, all over 10 factorial. 10 factorials cancel and we're left with 13 times 12 times 11, which is 1716. Now we use the factorial function to find out how many different ways objects can be arranged. If we have a set of n different objects, we can find out how many ways they can be arranged. When we consider the first place in the arrangement, we can choose one out of n objects. There are n options. Once we've put an object in the first place, there'll then be n minus 1 objects left for the second place. And there'll be n minus 2 objects left for the third place, and so on. And so finally, there's only one option, one object left for the last place. So the total number of options is n times n minus 1 times n minus 2 times n minus 3, and so on, down to 3 times 2 times 1, which is in fact n factorial. So, if we've got n objects, they can be rearranged in n factorial different ways. Let's have a look at some examples. There are two ways that two objects, A and B, can be arranged. It can be written as AB or BA. So the number of arrangements is 2, or we can write that as 2 factorial. Three objects, A, B and C, can be arranged in 6 ways. Starting with A, we've got ABC and ACB. Starting with B, we've got BAC and BCA. And starting with C, we've got CAB or CBA. So the number of arrangements is 6, which is 3 factorial. 7 objects, A, B, C, D, E, F and G, can be arranged in 7 factorial ways, which is 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5040. So we have the number of ways n different objects can be arranged is n factorial. An arrangement of objects is also called a permutation. Now remember, there is a factorial button, an exclamation mark, on most scientific calculators. It is worth finding out where it is on your calculator. It'll be above one of the buttons and you use the shift button. So typing 6 factorial will give the answer 720. Let's have a look at an example. The four kings, the king of clubs, the king of spades, the king of diamonds and the king of hearts, are taken from a pack of cards, shuffled and then laid out in a row. In how many different arrangements can there be? Well, to solve this, the number of arrangements is 4 factorial, which is 4 times 3 times 2 times 1, or 24. In part B, the 13 hearts cards, that's the cards with a heart on them, are taken from a pack, shuffled and then laid out in a row. How many different arrangements can there be? Well, the number of arrangements is 13 factorial. And rather than multiplying all that out, it's better to use the calculator button. So 13 factorial gives 6,227,020,800. In part C, we're asked the 4 kings are laid out, followed by the 4 queens in a row. How many possible arrangements are there for this? Well, the kings can be laid out in 4 factorial ways. And then for each of these, the queens can be laid out also in 4 factorial ways. So the total number of arrangements is 4 factorial times 4 factorial, which is 24 times 24, or 576. So our answer is 576. Let's look at a different example. If 4 girls and 6 boys lined up in a queue, how many arrangements could there be? Well, there are 10 children, so the number of arrangements is 10 factorial, which is 3,628,800. In part 2, we're asked, how many ways could only the girls be arranged? Well, there are 4 girls, so the number of permutations is 4 factorial, which is 24. In part 3, we're asked how many ways could only the boys be arranged? Well, there are 6 boys, so the number of permutations is 6 factorial, or 720. And in the last part, part 4, if the girls were at the head of the queue, how many arrangements could there be? Well, if the girls are at the front of the queue, there are 4 factorial arrangements. And for each of these, the boys can be arranged in 6 factorial different ways. So the total number of arrangements is 4 factorial times 6 factorial, which is 24 times 720, or 17,280. So our answer is 17,280 ways. Now sometimes we want to arrange a list of items, but there may be repeats. There may be several items that are identical to each other. For example, suppose we have the letters in the word sleep. There are 5 letters, but one of them repeats. If all the letters were distinct, such as sleep, where we've coloured 2 of the letters, there would be 5 factorial possible arrangements. But for each possible arrangement, such as peels, where you've got a blue E followed by a magenta E, there'll be another where the magenta E comes first. And this would be, if there were no colours, the same. So there are 5 factorial over 2, or we could say 5 factorial over 2 factorial arrangements. So that's 120 over 2, or 60 permutations. Now, if there were 3 letters that were the same, such as in the word tatty, then for each arrangement of the letters in tatty, there would be 3 factorial similar arrangements. Now we can see this if we colour the T's as separate colours. If we colour them as magenta, yellow and blue, there are 2 with the magenta at the front, yellow before blue and blue before yellow, 2 with blue at the front, magenta before yellow and yellow before magenta, and 2 with yellow at the front, blue before magenta or magenta before blue. So for the 5 distinct letters there'd be 5 factorial permutations, but for each distinct pattern, when the colours are removed, there'll be 6 identical copies. So the total number of permutations is 5 factorial over 6, or we can write that as 5 factorial over 3 factorial, which is 5 times 4 times 3 factorial over 3 factorial, which is 5 times 4, or 20. So there are 20 possible arrangements. Let's look at another word. Consider the word abracadabra. It has 11 letters. There are 5 A's, 2 B's, 2 R's, 1 C and 1 D. So the total number of ways the letters could be arranged is 11 factorial, but we divide it by 5 factorial because there are 5 identical A's. We divide it by 2 factorial because there are 2 identical B's, and we divide it by 2 factorial again because there are 2 identical R's. So this is 11 times 10 times 9 times 8 times 7 times 6 times 5 factorial over 5 factorial times 2 factorial times 2 factorial. Now the 5 factorials cancel, and the 8 cancels with the 2 factorial and the 2 factorial to leave 2 on the top. And this leaves us with an answer 83,160. It would probably be quicker to use the calculator to work that out. Let's look at another example. How many ways can the letters in Mississippi be rearranged? Well, Mississippi has 11 letters. It's got 1 M, 4 I's, 4 S's and 2 P's. So the total number of permutations is 11 factorial over 4 factorial times 4 factorial times 2 factorial. Now again, we can write that out in full and cancel, or we can work it out on a calculator. And that gives us 34,650. Or on our calculator we could type 11 factorial divided by, in brackets, 4 factorial times 4 factorial times 2 factorial, close bracket, equals, and that will give the same answer, 34,650. Let's have a look at permutations with restrictions. Sometimes there are restrictions added when we're doing a permutation question. Let's look at an example. How many permutations starting with the letter N are there of the letters in banana? Well, the first thing to do is to consider the restricted positions and then work out the remaining permutations. So the first letter is fixed, N. And then we have 5 letters with 3 of them repeating. There are 3 A's. So we have 1, because the first term is fixed, times 5 factorial over 3 factorial, which is 5 times 4 times 3 factorial all over 3 factorial, or just 5 times 4, which is 20. Let's look at another example. At a party, a mother and her 2 children sit in a circle of 8 chairs, with 1 child on each side of her. Another 5 children sit in the remaining chairs. How many possible permutations are there? Well, to solve this, the mother first has a choice of 8 chairs. Her 2 children then have a choice of 2 chairs, depending on who sits on the right and who sits on the left of her. The remaining 5 children then have a choice of 5 seats. So the total number of arrangements is 8 times 2 factorial times 5 factorial, which is 8 times 2 times 1 times 5 times 4 times 3 times 2 times 1, and that's 1,920. Let's look at another example. How many different numbers can be formed using all the digits of 111223 if, now in the first part there are no restrictions? Well, there are 6 letters with 3 repeats and 2 repeats. So the number of permutations is 6 factorial over 3 factorial times 2 factorial, which can be written as 6 times 5 times 4 times 3 factorial over 3 factorial times 2 factorial, or 6 times 5 times 4 over 2, which is 60. So the number of permutations is 60. Now in the second part we have a restriction that the number must be an even number. To be an even number, the last number must be a 2. Now the remaining numbers are 1, 1, 1, 2 and 3. So we've got 5 numbers with 3 repeats. So the number of permutations is 5 factorial over 3 factorial, which is 5 times 4 times 3 factorial over 3 factorial, which is 20. so the number of permutations is 20. And in the third part we have the restriction that the number must be an odd number. So the last remaining number is a 1 or a 3. Now we'll have to consider these separately. If the last number is a 1, the remaining numbers are 1, 1, 2, 2 and 3. So we have 5 numbers with 2 repeats and then another 2 repeats. So the number of permutations is 5 factorial over 2 factorial times 2 factorial, which is 5 times 4 times 3 times 2 times 1 over 2 times 2, and that works out to be 30. If the last number is a 3, then the remaining numbers are 1, 1, 1, 2 and 2. So we've got 5 numbers with 3 repeats and 2 repeats. So the number of permutations is 5 factorial over 3 factorial times 2 factorial, which is 5 times 4 times 3 times 2 times 1 over 3 times 2 times 2, and that leaves 10. So we've got 30 permutations ending in 3 and 10 ending in 1, and that makes 40. So the total number of permutations is 40.